Let's talk about mass spectrometry. I want you to be able to diagram a mass spectrometer, tell us the various elements of the spectrometer and what it does, and how to interpret a mass spec trace to get the isotope mix of an element and its weighted average atomic mass as we find on the periodic table. Here's the problem that was discovered really fairly early in the 20th century. Dalton was right in that atoms are fundamental building blocks of every substance. But Dalton was wrong about something. He thought that all atoms of a given element are exactly like every other atom of that element. But he was wrong. The nucleus, of course, contains protons and neutrons. The electrons outside the nucleus give us the chemistry. But the protons and neutrons give us 99.9% of the mass. The protons of a given element are always the same for every atom. For instance, carbon has 6 protons. But the neutrons can vary, and most of the elements do have varying numbers of neutrons. So carbon, for instance, has 3, and there's the word, isotopes, atoms with differing numbers of neutrons. Carbon has, therefore, all of them have 6 protons. All the nuclei have 6 protons. But you have carbon 12, carbon 13, a very small amount, and carbon 14, the radioactive isotope that you may have heard about in biology or elsewhere. Let's look at bromine, which has only 2 naturally occurring isotopes. Bromine 79 with a mass of 78.918. Remember, that little difference is called the mass defect from our nuclear chemistry back in first year. So bromine 79 and bromine 81, which has a mass of 80.916. Do you remember how to calculate the weighted average atomic mass from the mass of an isotope and its abundance? You might want to do that now. If you didn't remember, you take the atomic mass of the first isotope, 78.918, and you multiply it by the decimal equivalent of the abundance, 0.5069. You then multiply the atomic mass of bromine 81, 80.916, and multiply that by the decimal equivalent of its abundance, 0.4931. When you add those two numbers up, those two products, you will take a look at the periodic table and see that you get the atomic mass of bromine given on the periodic table. Now, why would it be difficult to separate an element like bromine, or carbon, or hydrogen, or uranium into its 2 different isotopes? Well, if you look, for instance, at bromine, you see that the mass difference, the percent difference, is only a little over 2%, 2 of every 100 grams. In uranium, the difference is even worse, only a little over 1% between U-235, which is useful for fuel, and U-238, which is useless as fuel. The percent mass difference, again, a little over 1%. If you say, well, let's chemically separate them. Now, the problem is, for carbon or for uranium, for anything that is just a matter of separating isotopes, the chemistry of the isotopes is exactly the same. The reactions they undergo is not different. So what they do is they use ultracentrifuges, and these very, very high-speed, high-cost centrifuges then will precipitate out the heavier isotope first and the lighter isotope second. So you can do a series of centrifugations to make a more and more pure isotope. Well, that's okay for large amounts, but for small quantities, the mass spec is what we use, mass spectrometry. Now, you may not remember what happens to a moving charged particle in a magnetic field, but if we click on this, we can see over here on the right that I'm not sure if Java is going to work, probably won't. But you can see that as the charged particle moves through the X's, which is a magnetic field, it's going to be bent. Its trajectory is going to change. So it's going to move more in a circle. The mass spectrograph looks like this. This is a nice little thermo mass spectrograph. Give them a little free advertising here. And these things can cost a lot of money. They can cost $35,000 to $100,000. And you'll see why when I describe how it works. The sample of liquid or gas or whatever it is going to be vaporized. It's a gas, of course, it comes as a vapor to begin with. And you can see on the left that its pressure is very, very low, 10 to the negative 2 torr, which is very, very negligible pressure. And it's heated up and passed through an opening into an ionizer. The ionizer, first of all, is at a very, very low, even a lower pressure, 10 to the negative 7th torr. And this hot gas then is passed through an ionizing apparatus and given a charge. And as it exits, it is accelerated through an electric field. It then passes, the stream passes here into the magnetic field. Now the magnetic field is very, very high. So you've had to pay for the vacuum, you've had to pay for the magnetic field. Now, what's going to happen to these, say, a heavy isotope and a light isotope? Well, it's kind of like a nose tackle running, 300-pound nose tackle running. The heavier isotope, of course, is going to have more trouble bending in the magnetic field. And the lighter isotope, like a little running back, 200-pound running back, although that's not so small, is going to turn a lot more in the magnetic field. So what happens is, as the operator works the magnetic field, the low energy or the high mass particles are going to be detected on the far end of the instrument, and the lighter particles will be detected on the near end of the detector. That signal is then sent to a computer, displayed on a screen, printed out, so that, as you can see, on the horizontal, you've got the mass of the isotopes, and the detector is counting these hits as the ions hit the detector, and the number of hits is graphed on the vertical. So you have the relative mass along the horizontal and the relative number of isotopes on the vertical, and you get a very, very good trace. And you can click on, if you're on the screen, you can click on the YouTube video for the mass spec operation. This is the kind of thing that we get for bromine. Now, doesn't this look a lot like the numbers that you just got from the previous slide? The 79 isotope is more abundant than the 81 isotope is. Now, over here you see on the right the mass versus a percent. But that's not the percent abundance because they add up to 197.3. If you want the percent abundance, you're going to divide the signal, the strength of the 79 isotope, which is 100.0, by the total, 197.3. If you do that, you will come up with a percent abundance that is exactly what you see on the previous screen. And then you can work out the weighted average atomic mass for the bromine atoms. Here's another one for strontium. And you might want to stop the slide, stop the YouTube video, and estimate this is percent abundance. Estimate this will be about an 82 and this will be about a 7. Estimate these four and multiply for each one of the abundances times the mass. Multiply those to get the four amounts and then add them up and see how that compares with the periodic table and its atomic mass for strontium. I think you'll find that you can get very, very close, even just estimating what these percent abundances might be. Most of the time when you get a trace from a mass spec, you're going to get the numbers. You can look at zirconium and see the same kind of thing. Obviously, the 90 isotope is in the highest abundance, and the 94 is just slightly ahead of the 92. But here you have 5 calculations to do, and I would strongly suggest that you do those estimations. This is probably around 3%, and this is in the vicinity of 20%. Do those calculations and compare it with zirconium in your periodic table. And then boron, this is not a particularly exciting one to do, but you can work on this one as well. Turn the YouTube video off and do the calculations and compare it with what you see. Now note, this goes up to 100, so you're going to have to do what you did earlier on for the bromine, and you're going to have to add whatever this is, say 100, to this, which is probably about 25, and divide 100 by the 125 to get the percent abundance, or the decimal abundance, and divide 25 by 125 to get the decimal abundance of the 10 isotope. Chlorine, this is chlorine gas. Just wanted to point out that this is the result of 2 isotopes of chlorine. But remember, chlorine comes in packages of 2. It's a diatomic gas. And so here we've got 2 light isotopes together, here 2 heavy isotopes, and here you've got 1 of each. That's concluding our video presentation here on the mass spec.